I'm going to go ahead and get started. Welcome. My name is Tom Carson, and I am from Tennessee. I've taught at the community college level for, since 92, I guess it was, 91, 92, and also have taught high school level. And so this presentation is actually a culmination of just a fascination with the history of mathematics, and in particular with primary sources. And for me, it's really fun to present some common topics using primary source material, because I've found that as I've dug into the primary sources, sometimes what we think the mathematicians have said, or sometimes what we have been told, or the way we teach it, is not necessarily the way they presented it. And it's kind of fun to dig in, and that's some of the stuff that I'm going to show you today, is some of the ways things were presented. And I've found that actually that can be very interesting to our students. So let's dig in. I do want to mention, of course, that there is a handout. And so if you're coming in, make sure that you get the handout. And the handout looks like this. All right. And so I just want to call attention to some of the pages on the handout. The first page there is, we're going to get into why the primary sources. And there's just some room there for you to take some notes, classroom examples, and so on. And then the second page and third page, I won't blow this up too much, but these two pages are just some things that I have found that are still around, that you can actually still get copies of. So that's a list of all of the things that you can actually find copies of, sometimes even digitally online, and sometimes, and of course, hard copy. And some of the books that are going around are just those hard copy versions, but there are also digital versions. And we will also see many of the libraries have the real deals. And that's something else that I've kind of gotten into, is going to various university libraries and seeing what first editions they actually have. And that is a lot of fun. If you ever get a chance to do that, I would highly recommend it. All right, so we'll see actually a few of my photos of some first edition materials. All right, so the last page of the handout, just to call attention to that, on this last page, these are some websites that you might consider visiting that have some digital media of some first edition or some primary source materials. And the library that I tend to frequent, just so you know, is the University of Louisville. I'm from Tennessee, so it's just right up the road. And they have an amazing collection. If you're ever in Louisville, I highly recommend stopping by the University of Louisville. Their collection is unbelievable as far as rare books and first editions of mathematics texts. All right, so let's dig in. So why primary source materials? Well, I think one of the things that's neat about primary source materials is it shows an unfolding story of mathematics and human experience. So I think it's important for students to see that unfolding story, and that mathematics is actually great literature. And when you read some of these authors, you find out that the prose is actually very sometimes entertaining, sometimes, yes, it is kind of dull. It just depends on the particular author. But it's really interesting, I think, to see the prose. And that's one of the things that the students are often surprised about, is that the style of writing is much more prose, much more paragraph style. You don't see, sort of the algebraic steps like we often see today. You see just big paragraphs of sentences with mathematics in them. And that's often fascinating to them. And I think it's also interesting to remember them as the great thinkers that they were, and they were often much more than just mathematicians. Oftentimes they were polymaths, we would call them, interested in science, philosophy, literature, as well as mathematics. So they contributed in multiple arenas, even though we tend to specialize and think about just that portion that matters to us as mathematicians. It's interesting to bring to light to students that they had so much more to do and so much more to think about than we often give them credit for. And I think it's also important to expand the conversation and show that interconnectedness of ideas that they often presented. For example, Pascal, that we'll look at, often applied his mathematical thinking to his philosophical thinking. There's a great passage in his Pensées that's called Pascal's Wager, where he actually kind of applies that wagering stuff that he was working on with Fermat to an apology or apologetics of Christianity, which is a really neat approach. And of course, novelty, I think, builds enthusiasm, and that's one of the great things that that I find with students is when you start bringing in some of these kinds of things, even an old book or something, that novelty builds interest and enthusiasm. So let's look at some primary source materials. So the first one I want to start with is Euclid. And if you came to the session last year, I spent more time on Euclid. Today I'm just going to kind of do a quick view of some Euclid materials. This is actually a first English edition of 1570, and this is one from the University of Louisville, and I took these photos, so forgive some of the lack of definition. They allowed me to take some photos. But some neat things that you can do in the classroom is discuss the undefined terms concept is often kind of an interesting concept. And this is actually Euclid uses definitions, and of course nowadays we kind of call them undefined terms. And I think another neat one for students to see is his proof of the Pythagorean theorem, which is rather extensive. And it's not the easiest thing in the world to get through, to wade through, but I think it's neat for students to see how different proofs are out there. Right? And so Euclid's proof, of course, is where you're showing this triangle here congruent to this triangle, and therefore because they have common bases to this square and this rectangle, those two areas are the same, and then you do the same thing for this triangle, and therefore this square and this rectangle are the same, and so these two square areas are congruent to these two rectangle areas, and therefore these two square areas together make the square area there. And that's Euclid's approach overall. And of course, he takes a bit to say that. But again, this is the first English edition of 1570. One of the neatest things, I think, in this edition, whoops, let me go back closer. One of the neatest things, I think, in this edition is finding out that he also does the golden ratio, and that it's not just geometry, so to speak. He does a geometric approach to the golden ratio, but this is my favorite piece of it. This is 1570, so if you think about printing, it just come into being with the Gutenberg press in 1455, 1450s. So within 100 years, they're already doing pop-ups, okay? And that's the neat thing here, is that in order to show some of the solid stuff, they began using pop-ups, and that's what this is. There's a little pop-up in here, and it's amazing to me that a 1570 copy, that's still in that good a shape. And that's one of the other things that's really neat when you start looking at these actual editions, because they were printed on parchment and not on paper, they last. Parchment is skin, it's animal skin, okay? So they really do last. In fact, when I go to the University of Louisville, you don't even have to wear the white gloves that you sometimes see because it's parchment, it's gonna last. So it's really amazing, the condition. I have some books from the 1800s that are in terrible shape because they're paper, and they're kind of falling apart, versus these things, 500-year-old books almost, and they're in fantastic shape. So, all right. Let's get into some of the ideas for the classroom then. Besides Euclid, last year I talked about Ptolemy, but I wanted to mention him again, that just to kind of go through some of the things that you could do with some primary sources. Ptolemy is kind of neat for trigonometry. What I often do with my students, I'll show them how Ptolemy's trig table, which is chords actually, it's not sines and cosines like we're used to seeing, but his chord table is actually quite accurate. And it's neat to go through that process of showing students how to convert the chord value into, say, a sine value, and let them see how accurate his table is. It's also interesting for them to see that Ptolemy's approach to fractions is rather different than we would say now. Of course, the Greek approach to fractions was in terms of the sexagesimal system, where you have 60ths, 3600ths, and so on, and every fraction would have been written in terms of those. So they have to also do some interesting conversions with the fraction values to get it into a decimal system that they can kind of get used to seeing. But that's kind of fun, I think. You could also go into Diophantus, which is somebody I'm going to talk about today. And so I'm going to dig in more detail with Diophantus, but I think one of the neat things there is the word problem that's associated with his age. We really don't know much about Diophantus except for that word problem. And then discuss the Diophantine equations, which I think is really neat. But the funnest thing that I've done with my students is showing them the notation, the Greek notation that he began using, which was actually an improvement, but it's still a little bit quirky. But it's still fun, and students can quickly grasp how it works, because it's not that different. It's just in terms of Greek letters, and I'm going to show you that, how that works. We'll also talk about algorithmy. And I think one of the neat things about algorithmy, of course, is so many of our words, like algebra, of course, come from him. And his name became the word algorithm. So when we talk about an algorithm, that's coming from his name, algorithmy. It started out as algorithm, and then kind of morphed into algorithm later on. It's also neat to see his method for solving equations, which of course is what we now call completing the square. And so we'll get into some algorithmy. And then the other person that I want to show you, although I brought Fibonacci, I decided not to show Fibonacci today. But there's a lot that's out there about Fibonacci, which is why I decided not to show him today. But of course, you can do the Arabic numeral system and tell that story. And show the original famous problem, which actually is this problem buried deep in the book. It's really obscure, and it's in chapter 12, so you could easily overlook it. But this one problem that built such, this interesting sequence that everybody makes so much about, Fibonacci, it wasn't that big a deal. It was just a problem among hundreds of problems, okay? And of course, he also has some other neat things. He shows actually Diophantus and algorithmy. He refers to algorithmy because really this work, Fibonacci's work, was kind of the gateway of algebra into Europe, okay? And so he kind of presents algorithmy and Diophantus and the algebra to Europe. The other person that I really want to focus on today, though, is Pascal. And so we'll talk about his famous triangle, and we'll see some of the things that are different about the way he worked with his triangle than maybe what we're used to seeing today. And that's part of the story that I want to convey, is that sometimes what we think people said or what we think people did is not quite exactly what they did. And so we want to play with that. For example, Descartes. If you look in Descartes' work, we tend to think of Cartesian coordinate system as having an x and y axis, and away we go. Well, if you look in La Geometria, his geometry work, it's not there. You don't see an x and y axis as the first thing, and he describes coordinates, and off we go. It's not like that, which is kind of interesting to see. So let's dig in a little further, and I'm going to switch over to PowerPoint now, and we'll dig into Diophantus. I'm switching to PowerPoint, by the way, because it serves better what I want to show. So Diophantus, what we know about him is he was an Alexandrian and lived around 200 to 285, 201 to 285, somewhere in there. And he's known as the father of algebra. And the only thing we really know about his life is from this word problem that came later. And it's kind of a neat word problem that you might consider filing away or giving as a bonus question or something like that if you're doing systems of equations. It's kind of a fun problem to solve. It says his boyhood lasted a sixth of his life. He married after a seventh more. His beard grew after 1/12 more, and his son was born 5 years later. The son lived to half his father's age, and the father died 4 years after his son. And so the problem, of course, is to figure out what is Diophantus's age and what is the son's age. And so you can actually build a system, something like that, and then solve that system. And we get that he was 84 when he died, and his son was 42, following that system. So let's dig in a little bit about the Arithmetica, which is his best-known work. And it was actually 13 original books, of which we now only know of 6. So there's lost books of Diophantus that have never been found, and we think they were even lost as early, a couple hundred years after his life. Hypatia makes some commentary on Diophantus's works, and she only discusses 6 of them. So we think that they were lost already by her time. Some people even contend that maybe the 6 really are still the 13 and they just got broken up differently. There's different theories on what happened to them. But one of the things that's interesting in the work is, of course, this improvement on the Greek notation. If you don't know about what Greek notation, how it worked, numerals were actually their letters, and they would indicate a numeral 1 with an alpha, and usually like a little apostrophe sort of next to it. Diophantus uses a little different notation that we'll see. And then he also brings into variables. And it's actually pretty easy, once you kind of get used to it, to translate it to our modern notation. And we'll do some translations. And then, of course, he's also best known for the Diophantine equations. And many of you probably have heard the famous story of Fermat reading Diophantus and coming up with his, now what we call his last theorem, Fermat's last theorem. So let's look at some of his work here. This would be the way that he would have said things. He talks about to divide a given square number into two squares. This is Book 2, Problem 8, by the way. And his solutions are usually just specific cases. So he doesn't really generalize too much. So he actually has this specific case where he says, all right, given a square 16, x squared, one of the required squares, therefore 16 minus x squared must be the other square. So notice he's not using a two-variable system like we would normally think of. He's going ahead and kind of solving. In modern terminology, the way we would, of course, do that is we would say you've got z squared equals x squared plus y squared, something like that. And then say z squared 16, that's our given number. And we're going to split that into two squares. So y squared must be the 16 minus x squared. That's kind of a modern version of the way he said things. And then if we continue, he says, take a square of the form mx minus 4 all squared, m being any integer, and 4 the number which is the square root of the 16. So he's taking a perfect square trinomial, factoring it, and setting that equal to the 16 minus x squared. So in our terminology, we'd say that's the y squared is going to be an mx minus b form, and then we're going to set that equal to the 16 minus x squared and solve. Okay? And so when you solve that, you actually find out that and he solves it, he doesn't show steps in between, he actually just kind of says that becomes 5x squared equals 16x, and so therefore x equals 16/5, and therefore the two squares, if you square that x and the other number, you get 256 over 25 and 144 over 25. In our modern way of doing things, we would have shown the steps of that solution process. So I think it's kind of a neat approach. He doesn't completely generalize it, but he kind of infers and hopes that the reader can get kind of the message of how you might find some squares or split up a square number into some squares using this kind of process. All right? So that very problem that we just solved or just saw is the problem that Fermat saw that inspired him to say in his margin that on the other hand, it is impossible to separate a cube into two cubes or biquadratic into two biquadratics, or generally any power except a square into two numbers with the same exponent. I have discovered a truly marvelous proof of this, which, however, the margin is not large enough to contain. That is the famous quote that's there in the margin, and later editions of Diophantus, the editors would put this quote in those later versions, actually, right after this particular problem. So if you see a later version of a Diophantine text, you'll often see Fermat's quote in there as well, which is kind of neat. So let's look at the Diophantine approach to algebra. What would the symbolism look like? And so the numerals would have been the Greek letters, one for each numeral, and they would have had a little bar over them to make sure that you understood that that's a numeral, not a letter. Okay, so alpha bar would mean 1, beta bar would mean 2, and so on like that. All right. For variables, or to indicate a constant first, he would have used this monades is what it would have been called, and this symbol would have meant that you've got an x to the 0 term, meaning a constant term. So if he would put alpha next to that monades, it would mean x to the first. All right. Arithmos, using a end sigma, would have been x to the first, and so on. Dunamis would have been the x squared. And you can kind of see his symbolism. Dunamis, of course, delta for the d in dunamis, and the little gamma up at the top indicates that this is some sort of exponential. Okay. Incidentally, dunamis means power in Greek. It's the same word that we get dynamite from. I'm pronouncing it in the Koine pronunciation. Modern pronunciation might pronounce it dynamis, but it's the same word that we get our dynamite from, which was named after the Greek word power. So it's kind of neat that it has that extra function. Kubos, or cube, of course, means x to the third. And then the way he would indicate x to the fourth is dunamo dunamis. So that's two x squareds together, so that's x to the fourth. And an x to the fifth would be a dunamo kubos, so that's an x squared and an x cubed slammed together, which would be x to the fifth. So you can see he's understanding the adding of exponents. All right? And then a kubo kubos would mean an x cubed and an x cubed together, so that's an x to the sixth. All right? There were no signs for multiplication or addition, so you just slam things together, it means addition and multiplication going on, and you'll see how to distinguish those two things. There was a symbol for subtraction, and if you used the symbol for subtraction, everything that followed the subtraction would then become a negative term. So you really only used it one time, and all of the terms that followed it would mean negative terms or subtracted terms. And the word for is in Greek, estin, would have been the equal sign. So let's do some examples. So here's one. So if you have this in sigma, the sigma that comes at the end of a word was used. So that's an x to the first, and the beta is 2. So this actually means x times 2 or 2x. So it's actually not too difficult to translate. It's not that different from what we do. It's just now using Greek symbolism. So here's another example. See if you can get this. So this is dunamis, gamma. So what do you think that is? Any guesses? It's 3x squared, or x squared times 3. We would say it is 3x squared now. Here's another one. This is an equation because we now see the estin in there. See if you can get this. So we've got dunamis beta and sigma alpha, estin kubos dunami, or kumas delta. Got it? So it's 2x squared plus 1x equals 4x cubed. And here's a bigger one. Notice the subtraction symbol in there now. So what that means is all of these terms that follow, there's two terms actually here. There's the kubos beta, right, and there's the monades gamma that follow. So both of those are minuses is what that would indicate. All right, so if we see what this means, this would be 4x to the fourth plus 5x minus 2x cubed minus 3 equals 1x cubed. So no worries about writing it in descending order of degree like we would normally do. It's the 1 minus sign takes care of all the terms that follow until you hit the equal sign. All right? So it's kind of a compact, neat notation, actually, and it's not too hard to figure it out. And it's kind of fun to, once you show this to a student, it's kind of fun to get the students figuring out or translating them. They enjoy doing that. So let's turn our attention to Algorithm. And his compendious book on calculation by completion and balancing. And I'm not even going to attempt to pronounce the Arabic here, but the key words that I want you to focus your attention on are the Algebra and the Walmukabala. All right, Algebra, of course, is where we get our word algebra. And that's the word that basically means completion. And then the Walmukabala, or Al-Mukabala, is what means balancing. And so the algebra, or algebra, completion or restoration, has to do with adding or eliminating subtracted terms. So in Al-Khwarizmi's approach to algebra, if you had a minus or a subtracted term, you wanted to move that to the other side to make it a plus term on the other side of the equation. And of course, Wal-Mukabala is the process of balancing the equation with that moving kind of step. So it's kind of interesting that there are two terms of which we have kind of gravitated to the algebra term. But think about this. We could be talking about having Walmukabala 1 and Walmukabala 2 instead of Algebra 1 and Algebra 2. I mean, they could have, either word could have been chosen. So I think it's kind of neat that we ended up with the algebra. And so if you look at the organization of his book, and do remember that the books are floating around, so feel free to pass them around. There is an Al-Khwarizmi here. There's the Robert of Chester Latin, English side-by-side translation that you're welcome to see. But he solves 6 types of equations and then moves into geometrical demonstrations of those 6 types of equations. And then he actually gets into some expression manipulation, which is kind of fun to see some binomial manipulation that he does. And then, of course, there's applications. So it's very similar to a modern book, actually, in the approach. There's an appendix with some general rules at the very end. So let's look at some of the equations. The types of equations that he was working with were squares. They were basically quadratics. And so he talks about concerning squares equal to roots, concerning squares equal to numbers, roots equal to numbers, squares and roots equal to numbers, numbers equal to roots. roots and numbers equal to squares. So he had broken this down, the quadratics, he broke them into various types, in essence, or types of equations, and then solved them. And this neat quote that he says in there, furthermore, I discovered that the numbers of restoration and opposition are composed of these three kinds, namely roots, squares, and numbers. So basically, he kind of felt like most of the problems we're going to deal with can be boiled down to these types of equations. All right? So let's dig in. Let's look at one of his equations. So again, it would be prose, not so much the symbolic kind of form that we tend to see. So he starts out saying something like this: 1 square and 10 roots of the same amount to 39 dirhams. Dirhams would mean a denomination of money. So in our modern approach, we would say this is x squared plus 10x equals 39. In other words, roots, his use of the word root would mean the x. Okay? So then he gets into how to solve it, and he just jumps right in. He says you have the number of the roots, which in the present instance yields 5. This you multiply by itself, the product is 25. So for us, that's the completing the square process, doing half of the 10, then squaring that result, which yields 25. And that's, of course, what we then add to both sides. Okay, now he says it this way: add this to 39, the sum is 64. Of course, our equation would look something like that now, where we add that 25 to both sides of the equation, then we would factor it. All right? Now he says, now take the root of this, which is 8, and subtract from it half the number of roots, which is 5. The remainder is 3. This is the root of the square which you sought for, and the square itself is 9. And of course, the way we would do that is then take the square root of both sides. You'll notice something that we tend to jump up and down and wave our hands about to students. The plus and minus is gone. Well, he didn't consider the negative case. Okay, so at this time, mathematicians would have ignored or just completely disregarded the negative case. Now, he was aware of negative numbers because he talks about them, but he felt like they were useless in terms of solving here. There was just no need to consider the negative case. So that's why I left off the plus or minus. It's intentional. So please no emails that you left off your plus or minus. I was trying to mimic exactly what he does. Okay. Then he gets into some geometric versions of this. So he has a geometric approach to this, which you've probably seen before in this format, where you say that the x squared is a square of area x squared, and so the sides are x by x, and the 10x is a rectangle of 10 by x connected to that. And we're setting all of that equal to 39. Well, of course, the completing the square part comes from dividing that 10x rectangle in half, moving one of those rectangles sort of to the bottom, and you've then got an incomplete square. And that incomplete square, the side lengths are x and 5, right? And so what your objective is, of course, is to complete the little square that's missing, add that into it so you have a completed square. Well, you can clearly see that that little square is a 5 by 5 square, so its area must be 25. Therefore, that's what we add to complete the square. And now we see that the bigger square's sides are x plus 5 and x plus 5. So squaring that, of course, would give the area of the overall thing. Because we have now added the 25, the overall area is now 64. And you can see that's kind of where we got our equations from. That's how you normally see it. Al-Khwarizmi's version is a little different. So he actually takes the 10x and divides it into 4 little rectangles, and then distributes them around the square like that, which is kind of a neat approach. They're each now 5/2 x in area. And so you actually have 4 little squares around the edges now to complete the overall big square. And if you complete those, each one of those are going to be 25/4. Since there are 4 of them, we see that we're still dealing with 25, and so on. The process kind of goes from there. But it's kind of neat to see his version of it. It's a little bit different than what we normally see when it's presented in the geometric solution. And he does this for all sorts of, it's not just a one and done. He does lots of these geometric presentations of his problems, which is really fun. So he also gets into multiplying binomials, and this is an area that you don't often hear about or see with Al-Khwarizmi. So I wanted to bring it to your attention. He actually says, when therefore the nodes of numbers are proposed, either with some units or if units are subtracted from them, then the multiplication is fourfold. I.e., first, the nodes are multiplied by the nodes, then the units by the nodes, then the nodes by the units, and finally the units by the units. What's that? FOIL. That's exactly what that is. It's what we now call FOIL. Okay, and so then he gives an example, and he does one where we say we have 10 and 2 are to be multiplied by 10 and 1, and so he shows in a paragraph form what we would now show sort of in a binomial type format like that. So he does it numerically like that, and then there's the same kind of thing with variables. Okay, and so it's kind of the same deal. But I just thought it was really neat that the way he describes it is pretty much exactly the way we now describe FOIL, just in different words. But it's really the same exact thing. So I thought that was fun. I always like to also tell my students about the origin of, or the use of algebra in another context, because it's linked to the barber pole, okay? And if you aren't familiar with the origins of the barber pole, in Spain, so when the Moors conquered Spain and moved into Spain, the term algebra got used for algebrista. And of course, the term algebra, remember, means restoration. And so algebristas were the barbers of the day, okay? And so the algebristas also had a double function. So they not only served to cut hair, but they also set bones. They were basically kind of like your local physician. Bloodletting, bone setting, maladies, and so on, you'd go to the barber, okay? Because they're doing bloodletting and bone setting, it's a bloody business, they would have these, rags, of course, to wipe up the blood and so on. They'd wipe them out or rinse them out and hang them out to dry on the pole. And so you could always tell where the barbers were by the pole with the bloody rags. And so that's where the barber pole came from, is from the function of the algebristas being bone setting and bloodletting, okay? But I thought it was really neat that this term that we think of as algebra also has this meaning connected to the barber pole, and students always find that fascinating. So let's get into Pascal. So Pascal, in his treatise on the arithmetical triangle, which is actually a very quick read, I would encourage you, if you get a chance, to get a copy of that. It's easy to find a copy online even. And it's a pretty quick read, but it's really packed with interesting stuff. And so what I'm showing you here, this is actually from a 1654 copy, a digital copy of the triangle. And you can see already that it looks different than the way we tend to draw it now. We tend to draw more of a pyramid kind of shape to it. His version wasn't like that. His version was kind of this slanted sideways triangle with the diagonals being what we would now call the rows. And so he calls these top perpendicular values the bases, right? And these are the parallel values. And then you have these diagonals that are in there as well, okay? And so the flow of his work is he introduces the triangle, then he gets into what I would call interesting consequences. These are things like showing how the various numbers add together, and you've probably seen some of those, and I'll share some of those if we have some time to do so. And then he gets into finding combinations, which is what we tend to use it for today, as well as dividing stakes. And that's one of the things that we don't tend to talk about nowadays. And I want to try to show you how he used it to talk about dividing stakes. And then, of course, we're familiar with it for the binomial theorem. So let's dig into some of what he does. Of course, the number of each cell is coming from, in his case, doing a perpendicular and parallel together, which is a little bit easier to describe to our students if you have it in this format, to think of it as a perpendicular, contiguous perpendicular number with a parallel number added together to produce any cell value. And he does a neat little proof of his second consequence. He says in every arithmetical triangle, each cell is equal to the sum of all the cells of the preceding parallel row from its own perpendicular row to the first inclusive. So what does all of that mean? It means if you take this parallel, for example, add 1 plus 2 plus 3 plus 4, and then go down in an L sort of shape, you'll get the next, or you'll get the cell value in that L shape. Okay, sometimes people call this the hockey stick consequence. But he does a neat little proof, and I thought I'd show you the proof of that. So he's saying that these here add up to be that value, which the 10 is in the omega row. So he basically says that omega is equal to R plus C, so these two together. And then he substitutes, he uses substitution to substitute for C. C has got to be theta and B together. And then he just keeps back substituting like that until he gets the final value or the final equation. So if we then substitute for beta, beta is the psi and A together. And then A, of course, is equal to phi. So putting that all together, he's shown that his contention that omega is equal to the sum of all of these other ones. So that's that L shape. And he does that for all of these various consequences, which is kind of neat. He has these little proofs that he does. So the way we would see this today is in our pyramid kind of shape. And you would see kind of an L to it like that, which is, like I said, sometimes referred to as the hockey stick deal. So if you do any downward L, and it doesn't matter which direction, so like if we did this way, these numbers 1 plus 5 plus 15 plus 35 would add to be 56, which is kind of a neat consequence. So he does a bunch of consequences, and then he gets into a general method for finding any one of the values, which today would be our n choose r kind of approach. And the way he does it, of course, he doesn't have that formula that we're used to seeing. He actually just, in prose, describes it. He says, multiply all the numbers, the natural numbers preceding the perpendicular. So if we want to work with the fifth perpendicular, so the fifth perpendicular and the third row, which is this position right here, the fifth perpendicular, if you multiply all of the natural numbers preceding that, that's 1 through 4. All right? Then multiply the same number of natural numbers beginning with the row number. So since we have 4 entries here, or 4 numbers we've multiplied, we're going to multiply 4 numbers starting at 3 as well. So that's 3, 4, 5, 6. And then he says basically you divide those. And of course we see that what we cancel out would be the 4 times 3s. So we got 6 times 5 is 30 over 2 is 15. And that's getting the general number. And that's how you can generate any one of those numbers. Well, nowadays, of course, we recognize that as our n choose r formula, okay? And so Pascal's example corresponds to 6 choose 2 or 6 choose 4. And of course, it can be either way depending on which way you're going along this diagonal, right? And here's the neat thing. Normally, we go sort of a left to right, right, where we would call this n choose 0, n choose 1, or sorry, 6 choose 0 and so on all the way up, right? What he does is sort of, I think, backwards. He starts from the top and works down. So in actuality, this is his 6 choose 2, not his 6 choose 4. Okay? It's the same value, but it's interesting that he starts sort of from the right or the top and works the other way. So he then gets into combinatorics and he starts describing in terms of 6 or 4 letters how many different ways you can pair up those 4 letters. And of course, there's 6 ways you can do that. And so we're choosing 2 items out of the 4. And so that corresponds to 4 choose 2. And he points out that the way you find that in the arithmetical triangle is the number of any cell is equal to the number of combinations of a number less by unity than its parallel exponent and the number less by unity than the exponent of its base. What he's basically saying is that you add 1 to the 4, add 1 to the 2, and that's going to tell you what cells to look at. Okay? In other words, the 4 and 2, add 1 to each of those, so look at the cell with coordinates 5, 3, essentially. So if we go to that cell, this is row 3 and diagonal 5, and they crisscross at 6. Okay? So he uses that kind of approach to it, which I think is really interesting. Or he has an or in there. He says you can also do this. You can take the sum of the cells in the second row through the fourth. So if you want to use the 2 numbers that you're working with, you can actually do that. And so you could use the 2 and go up to the 4th diagonal, which is here. So you're going to go row 2 and add those 3 numbers that go up to that 4th diagonal value, add those together, and that gives you the 6 because that's the hockey stick shape that we learned earlier, right? So it's kind of neat that he shows you 2 ways to get there. So it's interesting to me that for Pascal, the triangle works along the diagonals from the top, not sort of left to right like we're used to it, all right? So 4 choose 0 would be this top position along this diagonal. 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4 would kind of go along like that. We tend to go the other way with it, right? So for Pascal, the cell of the 3rd row and 5th perpendicular that we talked about earlier actually does indeed mean 6 choose 2, okay? And using his version of how you do that, you would add 1 to each of those and make it go to the 7th diagonal and the third row, and that would hit the 15. All right, so how we do it nowadays, of course, we tend to describe it in terms of just sort of disregarding the top number or calling that row 0, then row 1, row 2, row 3, row 4, so that we get to a fourth row from 0, and then go to the second term, which is actually 3n, which is kind of interesting. So maybe using Pascal's method would make more sense to students to describe it as just add 1 to each of the numbers and really go to the 5th row and the 3rd entry. Because I always, whenever I show students this, they always say, well, isn't that the 5th row and isn't that the 3rd entry? And I have to spend some time going, no, well, if you start at 0, you're here, and so on. So it's kind of caused me to maybe rethink Pascal was onto something. It's easier to kind of think of it by just adding 1 to each number and going to that row and to that entry, and you got it. Kind of neat. Now, let's talk about dividing stakes. He gets into dividing stakes, and this is really interesting to me. He talks about dividing stakes between two players who separate before completing an agreed number of games. And this was presented to him by one of his friends who was into gambling, and gambling was a big pastime. And so they were into gambling, and they were concerned about, well, you know, what if the game breaks up before we're done? How do we divide up the stakes? How do we divide up the bet? And that's what this is all about. And he begins corresponding with Fermat about this very thing. And as a result of corresponding with Fermat, he comes up with this idea. And basically his premise is that the winners and losers shares, you should put those together and then divide that in half. And that would be a reasonable way to divide up the stakes. So if you kind of follow this table, now he doesn't do a table. I found it easier to present it in a table here, but basically he talks about it in terms of how many games you lack before a winner is determined. So if player 1 lacks 1 game and player 2 also lacks 1 game, they're both 1 away from a win. So basically they should just sort of divide everything, right? Because if player 1 wins, he gains it all. If he loses it all. So by Pascal's approach, then you would add the potential winnings and the potential losings for that player, cut that in half, and that's where we're getting the half. So that's how I'm doing this, the rest of this table, and he goes into each one of these cases. He says, well, what if player 1 is 1 game away, player 2 is 2 games away? Then if player 1 wins, of course, he wins it all. But if he loses, they're back to even again, so they should split the winnings. So if you add those two amounts together, that player 1 has the potential for winning, that's 1 plus a half, and then cut that in half, that gets you to 3/4, and so on. So he then connects it to the table, or to his triangle, and he basically says, what we're going to do, if player 1 lacks 1 game and player 2 lacks 2 games, add those two amounts together, that's 3, and that's going to tell you which diagonal to pay attention to is diagonal 3. If you then add those values in diagonal 3, in other words, add the cell values together, that gives you the total winnings that are possible. In this case, 1 plus 2 plus 1 would give you 4 total possible winnings. And then the way to divide it up is player 1 wins the sum of contiguous cells that player 2 lacks in games. So if player 2 is lacking 2 games, then player 1 gets these 2 cells. Remember, he works from top down, so player 1 would get these 2 cells. Player 2 would get this cell, and that's the way you divide it up. And notice that corresponds to what we figured out in the table. Player 1 would get 3 out of the 4, so the proportion he would get is 3/4. Player 2 would get 1/4. And then he goes into other examples. And so, for example, this one, if player 2 lacks 2 games and player 1 lacks 2 games and player 2 lacks 4, well, add those together. That means we're in row or diagonal 6. So if you add that together, that gives you 32. So that's the total possible winnings. And then so player 1 wins the 4 cells because player 2 was lacking 4 games. So player 1's going to get those 4 cells, and player 2 is going to get the other 2 cells that player 1 lacked. And so if you add those together, that gives you the portion of winnings that would happen. Okay? So player 1 would get 13/16 of whatever the bet is. Player 2 would get 3/16. It's really ingenious, I think. And then, of course, the last thing he gets into is what we now think of as the binomial theorem. And to me, I think it's just, this is one of the things we use the most nowadays. And for him, it was the last thing on his mind. It was more interesting to him to get into the whole dividing stakes and all that kind of stuff. And it's more of like an, oh, by the way, you can also do this whole mathematical deal. And it's kind of like he does a quick job with it. And that's the binomial theorem. So I think it's kind of funny, to me at least. I find it humorous that it was an afterthought for him. So let me show you a couple of the interesting things that you can do with your students with the Pascal's triangle. You can consider the sum of rows. And so if you look at the sums of rows, it's fun to sometimes just give students something like this and ask them what pattern they see. So what pattern is that? What do you see? It's going 2, then 4, then 8, 16, 32. It's 2 to the n, right? And if you take prime rows, this is another kind of a neat one. That's all entries in a prime row other than the ones actually are divisible by that prime, which is kind of neat. Consider the digits in a row. So if you make numbers out of the digits, do you catch that pattern? It's getting a little more difficult. These are the 11s, right? So it's 11 to the n, just by putting the digits together, which is kind of neat. And that's kind of neat to propose to your students. What do you do in the next row where you've got a 10 and a 10? And of course, you then have to carry to get the product. So you can still do it. You just have to carry from those 2-digit entries into the next entry. Some of the diagonals is fun. Now these are special diagonals, so you have to really be careful how you draw these. Do you see that pattern? Fibonacci sequence. If you look at certain rows, this first diagonal going this way is the natural numbers, then here those are triangular numbers. And if you look at pairs of triangular numbers and the sums, it's kind of fun. You get the squares. So adding 2 triangular numbers gives you a square. And then this is one of my favorites. If you look at some geometrical figures, if you put a single point on a circle, that's going to be 1 point. If you put 2 points on a circle and connect them, you've got 2 points, but you also have 1 segment that you can make. Put 3 points on the circle, you can make 3 points, 3 segments, and 1 triangle. 4 points, you can make 4 points, 6 segments, 4 triangles, and all of a sudden you start to see the values in the Pascal's triangle appear. So the entries are basically, if you discard the set of the ones, that's the number of figures that you can make by doing that placing of points. And so a circle with 6 points would have 6 points, 15 segments, 20 triangles, 15 quadrilaterals, 6 pentagons, and 1 hexagon, which is kind of fun. And then, of course, there's Sierpinski's triangle. And Sierpinski's triangle, of course, is that fractal where if you remove an inverted triangle at the halfway points of each of the triangles that are left, and you keep doing that, you have that figure. And of course, the neat thing about Pascal's triangle, if you cover up all of the odd numbers with a triangle, voila, there's Sierpinski's triangle appearing overlaid on top of Pascal's triangle. And I just think that's brilliant. So thank you very, very much. And if you are interested in some of this, the Prezi presentation that I had to begin with is available. And so you can go to prezi.com, user T. Carson, and that has all of that Prezi portion of it. And if you want an additional handout, feel free to email me, and I'll be glad to send you a handout. But thank you so much for your time, and hope you have a great conference.